All right, today we're going to talk about one of the options you have in your project, and that is to use the SD card as file storage. And so our first step in being able to make the SD card a file system is to look at the low-level physical hardware associated with mass storage. And so a secure digital card is essentially a flash memory in a way that's almost identical to the flash memory that exists on your processor, which means the operation of a flash is what are the things you can do to flash memory? You can do two things to flash memory. And it has to do with the words EEPROM. Okay? So if you look at the symbol EEPROM, what did the EE stand for? Okay, that's one of the E's, is erasable. Electronically or electrically erasable. Okay, so that's one thing you can do with a ROM, is you can erase it. Okay, so you can erase it. What's the P stand for? Programmable. And it turns out that's the second thing you can do with it. And it turns out that you can't program once. You can only erase to 1 and program to 0. So what we're going to do is we're going to take a block or a sector or a byte or the whole thing and erase it to 1. And at the time I want to store something, I'm going to put the zeros into the spot. And if you watch, when you download your program to the Launchpad, you can see that two-step sequence. You can see that it will first erase, and then it will program. And actually, it's a third step. It will verify that it has programmed correctly. And that will happen here as well. So there are two steps, which means that if you have a file and you want to change the file, what do you have to do? If I have data stored on the SD card and I want to change it, how do I?
You have to read it, then erase it, and then write it.
Okay, so if I want to set a bit, he said read, erase, program, and I was just going to say erase program, but if you want to just toggle a bit, you'd have to read the thing, erase, read what is in there, erase it, and then change it, write it back. So, or if you're in a file system, we won't read it. Well, if we want to write a sector, we're just going to erase it and then write it. You've seen what they look like. It's really tiny. It sits in the top. There it is, sitting right there. What I do is I have a big, something that looks like a big mini SD card. It looks like a big one, but it's actually, it's got a hole in the end for my micro. That allows me to plug it into that laptop. My Surface will actually take the micro. Okay? Because in order to use it, we need a laptop or some sort of formatter, okay? Because the microcontroller itself will not be able to format. I have had various lucks with the devices. The current driver that's downloadable actually works with the newer cards. Formatted in the newer way. Now, it used to be the new ones didn't work and the old ones worked, and now it turns out the newer cards work and the older ones do not. So if you're having trouble with it, I'd encourage you to try a different card before you give up totally. There it is, sitting in there. The wiring from lab 4 to 2 and 2, 3, 4, and 5, the new wiring is to connect up the receiver input and a chip select. Now, in lab 8, I'd encourage you to, in your first pass through using the SD card, use this exact connections so that when it's time to make sure it works, you know that it's either you've got one of these 10 wires not connected or you've got a card that wasn't formatted. And then when you get on to lab 11, the ones that I've seen so far, most of you are using a different pin for the card, the chip select for the SD card. And that's okay. The software is easy to change. And so you can move this pin to somewhere else. Okay? Questions on the hardware? This is one of the bad design practices, or one of the good design practices, depending on how you think about it. Both the SD card and the LCD use the same SSI pins, but the way it will switch from one to the other is the card selects. So if you look deep into the software, it actually shuts one down before it pulls up the other one. So it has to reinitialize the SSI port every time it switches between writing out to the graphics versus writing or reading from the display. Which means, is it critical? Are these two operations critical? Is this a critical section? Oh yeah, this is the biggest critical section you can imagine. Not only does it share memory, it shares I/O devices. Okay, so you got to be careful that that whatever you're doing with the SD card and whatever you're doing in the graphics, don't try to interlock with each other. And the easy way to do that is what? How do you get two threads to not? How do you get two threads to be atomic relative to each other? Okay, I hear mumbling, but I didn't hear an answer. How would you do it? No, semaphore is way too complicated. Well, semaphore would be needed if you had an operating system and it were really complicated. This is Lab 7. It's not complicated. Lab 8 and 11, not complicated. Semaphore is a lock. No locks, no semaphores. No priority. Okay, what did I tell you way back in Lab 2 about the LCD? Do you remember where I said to put the LCD software? Where?
Not in the background.
Not in the background, in the main program. Okay, we put way back when they're doing the alarm clock. We put you should have put the LCD software in the main program. And why did we do it? Why did I stop my feet and make a big face and said, don't put the LCD software into the interrupt service routine? Slow. It's slow, right? It takes milliseconds to do an LCD output. Okay. Well, welcome to the world. It takes milliseconds to do the SD card stuff too. Okay. And so now, does anybody see how to get the two systems completely separate? And never interrupt each other? No priorities. A priority is something you assign to an interrupt service routine. Put them both in the main.
Effectively the same priority.
Okay, fine. Fair enough. Sean wins. He's right. So it's effectively the lowest priority is to put them into the main program. Now, if we have an operating system, we'll have multiple main programs. In which case, we'll need a lock or a semaphore or a way to share, because there you would like to have one main program doing the SD card, a second main program doing the LCD, and you could essentially get in trouble if you had an operating system that switches those two main programs. But we don't have no operating system. We have one main program. Put them both in the main program. They will not interact with each other. Okay? And so you'll be fine. Now, just as always, we're going to communicate from the interrupt service routine down to the main program to say, now it's time to output some new data, now it's time to do a file. But the actual file input output and the actual LCD output, they're both occurring in the main program, so there's no way for them to interact with each other. Now, you've seen this before, and when I ask this on the next test, what am I going to ask? What magical word am I going to make you know? You see this? The two magic words will leap to your mind, and that's the question he's asking on the exam. Set up and hold. Okay? A polarity in phase is a detail associated with SPI that you can forget. But you may never forget set up and hold, right? Because essentially what we have is one edge, which is changing the output, and a second edge, which is reading the input. And there's a setup time. Yeah, where are the setup times? Do you see them? If I said label this diagram with the setup time, which one is it? Oh, that'd be a great question. I'm going to ask that. It's on the next exam. Write it down. I'm going to give you this picture. I'm going to say label the setup time. All right? I'm going to say label the hold time, and then I'm going to say label the propagation delay. There's 3 arrows here, and you're going to match them. Okay? See them? Anybody not know the answer? Brave? Right? Obviously, that's the setup. There's the hold, and this is the propagation. Okay? All right. That's what you have to know here. You know, is it fast? Yeah. You have to know why it's fast. Why is it fast? It's because I changed the edge on one, and I changed the data on one, and I read it in on the other. All right. All right, so there are 2 SD card projects. One has a file system, one is low level. The one that has a file system also has the low level. So what I'd like to show you is disk.io.h. And you remember why this was the fun file to create? Right? Breaking up tasks between you and your lab partner and volunteer to do the .h's, because in a system, the .h's are fundamentally the best thing to do because
That's what we provide to the customer.
okay, it's the .h is the thing closest to the customer. Yeah, so you get the interface with the customer. Some people don't like people, but you might.
What it does, not necessarily how it does.
Yeah, the H is what it does, and not how it does it. So the H is the design. The H is the intellectual thought, and so not written in Valvano world, but it's written. But these are the operations. I can read the disk. I can write the disk. Okay, so it's disk write, disk read. As you know, to disk write, you have to erase and then read it. But that's yeah. So those, and there's an initialization. Yeah, disk initialize. So the low level. Okay, so the low level initializes. Let me show you how to change the thing if you want, and that's in disk.io.c. So if you want to know what's going on, then that one. But you've got to know how it works as well, so we're going to look in the C file. Okay, where are you? This one. Okay. Okay. Most of you have the one from ADA Fruit. Some of you bought it from Hong Kong and have it a different pin. It should work as well. But this is the logical way in which you can change the port for the chip select to another pin. So this is using port D bit 7. That's the address of port D bit 7's 4000-7200. There's the bit for port D. You also have to change the port D initialization to use a different pin. But again, your first pass through, leave it alone, but eventually you'll have to change that. Let's see, what else am I going to say? One of the most common ways it used to work and now no longer works is somehow you've disabled timer 5A interrupt service routine. This is not an option. The interrupts do need to be enabled. This thing does need to run periodically. So make sure whatever you're doing that you didn't inadvertently disable that timer interrupt service routine. Okay? So this has to run every millisecond in order for the disk to run in the background. So low level, if you're trying to debug the low level stuff, you can run in the main program, you can run a main program called simple unformatted test. You should only do this if you're having catastrophic errors, because this will actually unformat your SD card, and so everything will be destroyed. Everything will be destroyed on the card if you run this program. But if you're debugging and want to fix it, obviously you can reformat it. If what you want is just a little bit of storage, you want like a high score list, you want just like a black box kind of thing. You don't need a full file system. You might consider using the starter code flash 4C123. What that does is store data onto the flash of the microcontroller itself. Again, doing the erase and write. So you could have permanent storage. So in summary, what we got is a low-level driver. Any questions? All right. Keep that running.